Now it's working. I've had several technical problems with this, but I really want it to work because this is a pointer that everyone at home can see too, and it appears in the recordings rather than, I normally use a laser pointer and a, remote to advance the slides, and it's nice to be able to look at the same thing you guys are looking at rather than hiding behind the computer. So I thought I'd start, many of you expressed some interest in hearing more about or seeing more details in the derivation of the relativity of simultaneity formulae that you see in the chapter. Many of you said that it was the most confusing chapter to appear so far. Yeah, there's the most stuff happening with the derivations where you have to go back and forth from the diagrams and look at the equations and all that kind of stuff. But hopefully what we did yesterday helped you maybe not digest the whole argument, but at least see that every step is understandable at some basic level, rather than there being mysteries hidden in there. So we worked really hard to get what Merman calls Rule 4, the relativity of simultaneity. I call this the clock asynchronization formula because it tells you if two clocks are synchronized in their own rest frame, which of course is the normal way we use clocks, right? If you have a clock in the next room over, you're hoping it's synchronized with the one in here. Then, and we know the separation between those clocks, that's important, this distance L. So when they're sitting at rest, we need to know the distance L between the clocks along the direction that we're going to move. Then in a different inertial reference frame, say up here shown as this space pod B that's moving along the length separating the two clocks, they move, which moves at speed v, then the rear clock is going to be ahead. Now, what do we mean by the rear clock? It's easy to forget this because you might think, oh, here's B over here. The rear is back here. No, B is sitting there watching this thing go by. So here's what B is seeing. B feels like B is totally at rest. This thing is moving to the left. So what I mean by the rear clock is as you're watching those clocks come by you from the other person's point of view, which one's in the rear? That one, the rear clock is going to be ahead by a certain amount of time in its reading. That is L. That's the proper distance between the two clocks. That means the distance when they're at rest. V over c squared. Okay, and we practiced that on a worksheet. And we said, the qualitative takeaway, which is really the thing is supposed to blow your mind here. This is so different than the way we think of universal time. Things that happen simultaneously in one point of view, so a bunch of firecrackers going off all at the same time, but at different locations, happen not simultaneously in another point of view. So the one, they sort of go off in succession over there. So some of them are in the future, some of them are in the past. At a certain instant in time, at a certain location, this IRFB person would say, some of them are in the future, they haven't gone off yet. Some of them are in the past, they already went off. Whereas this other observer, IRFA, is saying they all went off at the same time. Here is something that we've already alluded to, but it's a slightly different formula, and often this is the thing we want to know, because, it's kind of nice to know how much the clock's readings differ, but often we want to know how long we have to wait for two things to happen. So this is going to be phrased in terms of, if you have two events that are simultaneous in one IRF, and they're separated by a distance L, that's the proper IRF, so in some IRF, they're separated by a distance L and they go off simultaneously. Then in another IRF that's moving at speed v along the line connecting them, how long do we have to wait between the one and the other, the one that happens first and the one that happens later? What's the time separation between the two? And the answer is pretty easy to figure out, right? If we know the clock reading difference, so I'm showing down here in B's point of view, here's two simultaneous events. Those two firecrackers go off when these two clocks read noon. And we're already from our formula able to deduce that the difference in these two clock readings are LV over c squared, this one being ahead. This one going to reach there a little bit later, right? Here's a picture of that later time. Okay, so this thing, B is watching this move to the left. And at this later time, of course, this one's advanced, it's already past noon, but both the firecrackers went off when the clock adjacent to it read noon. So here's this other one's had enough time to reach noon now, and that's when this other explosion is going to happen right then. So the other explosion happens then. The question is, in IRFB, of course, in IRFA, there's no question, they're simultaneous. In IRFB, how much does B have to wait between this first one going off over here and the second one going off over there? And the answer is, in B, well, the clock readings have to change by LV over C squared. That's a change in clock reading. So B has got to see the one that's lagging behind advance by LV over C squared. But that's not how long B has to wait, because those clocks are running slowly. They're moving with respect to V. So we've got to apply that time dilation formula to it. If this is the reading that's going to tick off on the clocks, then gamma times that is how long we have to wait. Okay, so even though that's just a very simple extension of the formula, I think this is worthy of its own rule name. Merman doesn't give it a rule because it's just a combination of the previous one with the time dilation. But so I call this time between events. It's just a different version of the same kind of idea. If events are simultaneous in one frame, in a different frame, how long do we have to wait between the first event and the second event when they're not simultaneous? And the answer is LV over C squared divided by 1 minus V squared over C squared, or gamma times LV over C squared. Okay? So the details are, if they're separated by a distance L in IRFA and simultaneous, then we have to wait this amount of time in a frame B that moves at a speed V relative to A along the line joining the events. And it's worthwhile remembering that in IRFA, B is moving a certain direction. Whichever direction B is moving, the one that it's heading towards is the event that happens first. So I phrase that here. The event in the direction that B is moving in A happens first. Okay, so that tells you not only how long you have to wait, but which one is going to be the one that happens first. So in this case over here, B was heading in this direction to the right as seen by A. So the one it's heading toward is in that B IRF point of view. This one is going to happen first. That's the one that happens first. Later on, this one's going to happen. That's why we had to wait for it to move over and see that one happen. Okay, questions on that slight extension, but worthwhile remembering as its sort of own rule, because it sounds very different. Difference between clock readings, and one is how long you have to wait between what would have been simultaneous events in a different IRF. Okay, so we're going to use that worksheet 2 that I just passed out, the new version, or the version that I just sent today to you if you're on Zoom. And it says here we're going to do A together. So let's look at 2A. I'll switch to my screen in just a second. But looking at the figure, well, maybe it's best to switch to the screen right now. Let me turn on the lights for the benefit of those in the room at least. Move the camera up a little bit and pin my video. Okay. Too close? Let's see. And why are we so out of focus? I would assume this has autofocus on. That's not good. I'm not even sure how to get it to autofocus itself if it's not doing it. You mean the light in the room? I don't think so. Still looks just as, oh, you guys are brilliant. You've done this before, huh? Okay, now that it's focused, I'm turning the light back on. All right, thank you for that. So the worksheet says Earth sends a crew on a spaceship to planet X Okay, let's draw it, the drawing on the, let me just make sure I know exactly where the edges of what you guys can see on Zoom are. It looks like right there is at the edge. So I'm going to draw a picture of what's happening in the Earth IRF view. That's what's shown on the left in part A of the worksheet. Here is Earth. Here is planet X. And we're told that, well, you know, it doesn't say it in here, but these two are at rest with respect to each other. It does say that. This distance, as measured in the Earth IRF, I should really say that explicitly, is 7.8 light years away. So this distance right here is a very big distance, 7.8 light years. Okay? And we're going to send a little spaceship, which I just show as a little pod going in this direction, at 0.8 C, 0.8 C. And at the instant when this leaves Earth, and it's moving at 0.8 C in that direction, okay, in Earth's IRF, simultaneous with the ship leaving Earth, notice I have to say, when I say something happens simultaneously with something else, I have to say whose assessment of simultaneous it is, because it now matters, you know. Normally, we don't hesitate to say, oh, I know what's going on now on Mars or something like that, but it can make a difference if you're going to compare with someone who's moving really quickly with respect to you. So from here, at this, there's an event. The ship leaves Earth. That's the description of an event. In the Earth's IRF, there's something that's happening simultaneously over here. And it's what? An asteroid collides with the planet X. In the ship's IRF, at the time the ship has just left Earth, did the asteroid collision event happen in the past or will it happen in the future? Okay, so from the Earth's IRF point of view, at this instant in time, there's a big explosion over here on X. That's the same instant I'm drawing there, same time that is happening. The ship leaves Earth and it happens at the same time. Now let me just briefly go back to the slides and have you answer that question, which is, given the information there, so we've said what happens in the Earth's IRF point of view. In the ship's IRF point of view, did the asteroid collision happen in the past or will it happen in the future? In other words, these people are here on Earth. There's another event that's being described. Asteroid hits X. Is that, we're assuming it's not simultaneous with it because it's simultaneous in the Earth's IRF frame. So it seems like it shouldn't be simultaneous. It should be either in the past or in the future relative to them just leaving Earth. What do you think? Past or future? Past. Let's look. The event in the direction that B is moving in A, in other words, this is sort of Earth. This is X over here in this point of view. I'm pointing at the screen now. And B is our little space pod that's heading over there. This is the event that's happening first in the other frame, right? They're simultaneous in Earth's frame, but in the other frame, the one to the right is happening. And so let's go back to the board here. This is the one that the ship frame is moving at in the point of view where they're simultaneous. And therefore, this one happens first. We could describe it as asteroid hits X. The other event, if this one happens first, the other event, which is ship leaves Earth, happens later. Okay, so if we think this one happens later and we're here in the ship thinking that's right now, it's later than something that happened right now on Earth as I'm leaving in that ship. If this one happens earlier, then when we're at this event right here, it must have happened in the past, right? If we're just leaving Earth on the ship, from our IRF's point of view, it must be in the past. Okay, and so the answer is in the past there. And the question then, the follow-on is how much in the past? And we've got all the pieces of information that we can use that formula. The formula says that we just derived, or the follow-on to the clock asynchronization formula says the time you have to wait in a certain IRF between this event and this one, well, this one happened in the past, so how much time we have to wait between this one and this one, according to these ship inhabitants, is given by the formula LV over C squared times gamma V squared over C squared. In this case, V over C is 0.8. Okay, so let's start plugging in the numbers there. L is supposed to be the separation between the events in the frame in which they are simultaneous. Well, that's given to us at 7.8 light years. So our L is 7.8 light years, and I'm going to write that in that peculiar way that we write light years. A light year is the distance light travels in a year, so we can write that as the speed it's moving at, c, times the amount of time that elapsed 1 year. So a light year is the same thing as a c times 1 year. Sometimes I just write it as c times year. That's L. V is 0.8 c. Okay. Hey, notice that's kind of nice. I have 2 factors of c upstairs and 2 factors of c downstairs. So it was good I didn't plug in 3 times 10 to the 8th. There was no need there, right? That c squared in the denominator can cancel against those ones. Now I still need my gamma factor over here. So I need to multiply this or divide by the square root, either way. Multiply by 1 over the square root of 1 minus v squared over c squared. And that's 1 minus 0.8 squared. Okay, so you can, all the other things in here are numbers except years. So I'm going to get a quantity of time we have to wait in years. Or in this case, how far in the past is it? And when you plug those numbers in, I get, you can check it in your calculator, 10.4 years. So it sounds really strange. You're leaving Earth on the ship, heading towards X. The event that Earthlings say is simultaneous with that event, for you in the ship, that event occurs in the past, 10.4 years ago. That same event that the Earthlings think is happening right now. Something should sound a little bit suspicious about that, and we're going to dig into that after the worksheet. But any questions on this before I set you loose on B, C, and D? Jack? Well, so here's the frame of the people traveling in the ship. This formula that was on that last slide that we did, right? Putting the factor of gamma in there, we determined was if the 2 events are simultaneous in the one frame, that's the Earth frame, then in the other frame, that's the ship frame, how long do you have to wait between the first event, we already determined that's this one, and the later event, this event? That's the same, that question is just a rephrasing of how far in the past is this event relative to this event? In the ship's point of view. You have to wait 10.4 years. So I'm saying they aren't even looking at a clock, but they would say, our best assessment of what it means to say something happened in the past or future is that this thing, it's a publicly identifiable event, happened a long time ago from the point of view or the usual way that we define what it means to be simultaneous or in the past or in the future. I know something sounds a little bit fishy about that, and we're going to dig into it after the worksheet, but.
So in the IRF of, let's see, ship at planet X, would read the time with or without gamma at planet X from the.
So you're saying if someone's moving with the ship like this, and they just happen to pass X at the same time that the ship passes Earth, and what would their clock read. So the idea is if the original statement of the relativity of simultaneity said, if there were a clock at rest with respect to Earth and a clock at rest with respect to X, and we assume they're made to be synchronized in the Earth X rest frame, right? So when we view them normally, then this ship moving in this direction, you can consider a whole line of IRF observers moving along with it, is going to, at any instant in time, see this clock over here being ahead because it's in the back of the train. You know, they feel at rest and they feel like this train consisting of Earth and X is coming toward them. The one in the rear is going to be leading. Lagging clocks lead in terms of their setting. It's leading by this, just the LV over C squared. Okay, but then we've got to ask, how long does that mean we have to wait? Okay, other questions before we start the worksheet? I'm going to put the Zoom folks in a breakout room, and please do your best to have some discussion on parts B, C, and D here. And I'll come check in a few minutes. Oh, Jacob's on Zoom today. Okay. So we're missing Muchiri. Just Muchiri, I think. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're missing somebody else. Oh, Jacob Walterman, that's what it is. Jacob's missed 2 days. I'm not sure what's going on with that. I'm going to put this slide up there because it is relevant. I know when you first see these things, you really have to cling to the text and think, what does that mean? Which way is that person heading? And that one happens first. So relative to this instant, it's in my past or whatever. How are you guys doing? Do we need to go over B together to be sure? Or are you feeling okay? Yeah? Let me just sneak into the breakout room so that they can see my camera, and then we'll talk about B, because this stuff is very confusing the first time, obviously, because it disagrees with our intuition. Muchiri, I'm assigning you to a room where people are working on a worksheet that I emailed today, if you can hear me. So it's going to ask you to join a breakout room, and that's where a few of your classmates are working on it. How's it going? Okay. Everett, how are you doing? Okay, good. Joseph, how are you doing? Okay. Well, we'll see. Maybe I should have written the final answers up on the board. I just changed this right before class, so I don't have my solutions written out for C and D yet, but we'll figure them out together. Yeah, so the time is going to be, the time difference will really, in both of these cases, be the same as it was in A, and I can't remember if that quantity is the same as A. You've already calculated, right? The only difference is whether you put the shorter L in or the longer L in. A, C, and D all say the things are simultaneous in the Earth IRF view, and therefore we're using the same L. So I think I agree with that. And the only question is whether they're in the future or the past. So here we're saying as this is coming up on X, the direction that it's moving in the Earth point of view, that means this one is going to happen for. Yeah, so you always, at least the way I wrote that rule up there that's in the box, you look at the point of view in which they're simultaneous. And in this case, that's the Earth point of view. And you ask the other frame, which way is it heading? To the one, which event is it heading toward? Well, in this case, it's heading toward the ship arrival event. We could say there are two events. Ship arrives at X and hurricane on Earth. And this moving IRF, from the point of view of in which where they're stated to be simultaneous, it's moving towards the ship arrival one. So that's the one that's going to happen first, according to the sentence at the bottom there. So if this one is now, and this one happens first, this one's still in the future. So I agree with that, right? That hurricane's going to happen in the future. And it seems like it should be exactly the opposite here. It should be the past down there. So it's actually going to switch because the direction the ship is heading all of a sudden changes from going right to going left. So if this one now happens first, if this one is current and this one's going to happen first, then, this one happens first, and now we're at this one. This one's got to happen later, and therefore this event is now in our past. If we're sitting right here in the ship, right, saying, oh, here we are, just leaving X. The one back at Earth happened first. Now here we are later in time. That means the one that happened back on Earth is in the past. For some reason, I find that, thinking through the language very confusing. Okay, I'm going to pull back the breakout room and we can finish discussing this. Let's see. Sorry, it takes a whole minute to close the breakout rooms, as you guys probably know well from other ones. So we just have to be patient before everyone's back in the same place here. Okay, welcome back from the great breakout room, and we're going to do C and D. Hopefully we've set them up so that they're not At least the calculation part's not too hard. By far the hardest part in this is stating whether it's in the future or the past compared to as assessed by the people in the ship here. So we've now progressed on and we're considering the event the ship arrives at X. So the ship is arriving at X and we're told to consider that simultaneous with that, as assessed by the Earth rest IRF, okay, so from the point of view of the Earth IRF frame, simultaneous with this event, back at Earth, there is a devastating hurricane. I'm not sure how to draw that, maybe a little spiral or something like that. There's a devastating hurricane back on Earth. And the question is, in the ship's point of view, as the ship is just about to arrive at X, of course, the ship feels like it's at rest, and X and Earth look like they're moving along as a unit away from it. So they're moving to the left. Relative to someone sitting in the ship who's there at that event, a ship arrival at X, where does this hurricane occur on Earth in time relative to them? Is it in the past or in the future, and by how much? So the by how much question, again, is answered by LV over C squared times gamma. And we'll find that we've already done this calculation. In other words, we have to ask ourselves to figure out what L means. It's in which reference frame were the events simultaneous? Okay, that was the Earth reference frame. In that reference frame, how far is it between the events? Oh, that's 7.8 light years. So this is 7.8 light years. This is 0.8 C. We already did this calculation, right? This was what we did in part A. So we get the same answer as in part A, 10.4 years. That's how far, either in the past or the future, this other hurricane event is going to be from the ship's point of view. Here's the ship just arriving at X. There's an event that happens on Earth that's publicly identifiable. Did it already happen, according to their assessment, or is it still yet to happen? It's in the future. Well, the mnemonic, or the way of thinking about it that I have in that rectangular boxed summary of this rule, is that you look in the point of view where the two events are simultaneous. That's the Earth IRF point of view in this particular case. And you look at the other IRF that you're going to shortly consider the opinion of about the order of events, and look in the direction they're heading and say, whichever event they're heading toward is the one that happens first in their assessment. So in this case, ship arrives at X first. Then later, hurricane occurs on Earth. So in this case, it would be 10.4 years in the future, relative to people who are on the ship, who are here present at this ship arrives at X event. This one over here, well, this one happens first. Therefore, this one is yet to happen. If we're sitting here in this ship, that's our now. And if this one's yet to happen, that means it's going to happen 10.4 years in the future. That's how long we would have to wait for it to be considered current in our point of view. Okay, questions on that one? And Zoom folks, feel free to just unmute and shout out your questions if you've got them. You're on the speakers in the room now. Any questions from the room here? You know, as most things in relativity, the calculations are not the hard part. It is thinking about how to use them in the correct way, because there's a lot of incorrect ways to think about them. Okay, now, we're told in D that the ship arrives at X, finds that X has been destroyed by a big asteroid. They were going to inhabit this colony out there, and so they immediately have to, essentially, instantaneously, they start heading back to Earth at the same speed relative to Earth. So in D, we're told to consider they're moving to the left in the Earth IRF frame at 0.8 C. And in the ship's point of view, it's the Earth and X that start switching. They've switched directions to 0.8 C. Of course, this is at rest, but after it's gotten in that frame, right? So the ship heading back to Earth, from the ship's point of view, is Earth is heading towards me. Okay, distances are still the same, though. And the question is, same thing. Look, they arrived at X and they immediately started going in that direction. So the event ship arrives at X and the event ship leaves X are really the same event, right? They're at the same place and they happen essentially at the same time. I mean, one is moments after the other, but we're going to imagine they just boomerang right off of there and come back. So here's the same event. So in the Earth's assessment, that event of them leaving was the same event as them arriving because they just immediately left. In the Earth's assessment, this hurricane is still simultaneous with them, okay? It won't be simultaneous from the ship IRF's point of view. Which one's going to be first? Well, the ship is now in the frame where these two events are simultaneous. The ship is heading this way. It's heading towards the hurricane now. That means the hurricane is going to happen first in this IRF. Hurricane's going to happen first. And therefore, if we're here, if this one's going to happen first, this hurricane over here, these aren't at the same time, right? If we're here and this one's going to happen first and we're sitting here now, it must have already happened, right? It's kind of hard to think about in language. That means it's in our past. And the calculation's no different. You know, the L is the same as it was before. So the only difference in D is that it's in the past. And that should sound very suspicious to you because in an instant of time where the ship arrives, well, I guess they're in my picture there, you know, the ship is going over to X and it immediately turns around and goes back in the other direction. Their assessment, they're claiming that a moment before when they were heading towards X, this hurricane event was 10.4 years in the future, and now just by virtue of changing directions, they're now claiming that it's 10.4 years in the past. Sounds kind of funny, doesn't it? It sounds almost unbelievable or like there's some sort of cheat going on here. How can there be any meaning associated with this? Still don't understand why the focus on this still is so bad. It just can't seem to focus on the chalk for very long. Maybe it is the lights it doesn't like. Okay, well, in any case, any more questions on that before we go back to the slides? Okay, let me share my screen again. So we're back to this is just a restatement, a different way of thinking about that information of the relativity of simultaneity. What we want to spend the rest of today on is sort of the amazing aspect of this. What the heck is going on with all of a sudden something going from being in the past by 10 years to the future by 10 years? I call this idea the conventional nature of simultaneity. In other words, the difficulty is if I say, oh, I'm imagining a galaxy far, far, far away, and I wonder what's going on there right now. Is an asteroid striking? Well, when I say right now, there's no way for me sitting here to immediately verify what's going on over there. I can't have an instantaneous camera link between the two and watch, you know, what's going on over there. If I wanted to find out, I'd have to wait a long time for light to get back from that distant source. So when you're far away from something, it's hard to directly know what's going on there. Now, we can make a definition of what's going on there. And the definition of what's going on there right now, according to me, is the best definition we can come up with for simultaneity. And that is, well, what we do is, if I want to know in a certain reference frame what's going on at the same time, we all have a procedure by which we synchronize our clocks, right? Maybe you're several light years away, but what I do is say, okay, we're here together. You're going to travel over there with your clock, and I'm going to send you a light pulse. When I send you the light pulse, my clock is going to read 12 o'clock noon on a certain day. When you receive the light pulse, well, I know how long it takes the light pulse to travel there because it goes at C, according to us, and therefore, I'm going to tell you when you receive the light pulse, you should set your clock ahead by so much because a lot of time has elapsed in that process. And then I'll be sure that my clock has elapsed by the same amount and we'll have them be synchronized in that way. Now that process is a definition. And so we're defining what it means for something to happen simultaneously. So if you're 10 light years away and I say, somehow some event happens on Earth, some hurricane happens here, and I want to know what was happening in this galaxy far away? Well, what I would do is say, well, I want to know what happens at noon. So I'm going to record here what happens at noon on a certain day. You're going to record, when your clock reads noon on that day, the same event. And then we can come back together and compare. We can't compare right away. We have to travel together and compare our notes. But that's what it means for something to be simultaneous. And there's no better definition of what simultaneous means for a faraway location. And the consequence of that, Einstein is showing, is that if things are simultaneous in one frame, then they're not simultaneous in another, and it leads to all of these strange situations. So here's a person sitting on Earth. This is a very distant planet, maybe X, that's in the same IRF as this person here on Earth, maybe. And this person, through this complicated, clock synchronizing mechanism and agreeing on what it means for something to be simultaneous, because we both have clocks that are synchronized, we've done that very carefully, this person can, at least later on when they get the data, they could say, when I had this thought, event X is now to me. When I had that thought, this event X actually was happening at the same time. That's a definition because of the clock synchronization procedure. But we're going to use that clock synchronization procedure to define what it means for a distant event to be simultaneous. So here's a person standing on Earth. X is at rest, and suppose they know, they're omniscient, and they know that this event happens at the exact same time as it does for this person. Now suppose the person starts running toward the event on the surface of Earth. Maybe not even very fast. Maybe they're going close to C, but what we're seeing from this formula right here, the LV over C squared, is even if you don't go very fast, if the L is big, it can make up for it, right? It's the product of L times V that's in the numerator there. And if V is small, well, it can still have a big effect if L is huge. So even this is technically true, even if someone's running at a normal speed. So this person runs toward whatever direction on Earth is, that event at X, and I'm asking the question, that event at X is when to me asking this question here on Earth. This is the kind of thinking we were just doing on the worksheet, so help me figure that out. In the past, so let's check it out. So let me think through it myself. The person who's doing the moving, so these two events are simultaneous, the person being on Earth and that explosion going off. So if we change to a point of view where we're moving towards that event, this event's going to happen first, and this event corresponding to the thinking over here is going to happen later, right? And that means that this event is in the past at X relative to that person. Okay, if you're not catching on to the logic of that, we'll do it one more time, but please ask, and I try to say it a different way. Okay, so here's that statement that we're doing. Looking at the last sentence, the event in the direction that B is moving in A. That means relative to the Earth X frame, which way is this person moving? Because the two events were simultaneous in the Earth X frame. This is the one that happens first. If this one happens later and this person is thinking it, that means this one already happened. It sort of makes you really twist your mind in that way. Okay, so far in the past to me. Similarly, if the person just runs in the other direction, all of a sudden their assessment is that this event hasn't happened yet. It's far in the future to me. It's not going to happen for a long time. Now it happened a long time ago. Now it's going to happen a long time in the future, and I keep changing my mind about that. That seems kind of absurd. Well, it's not absurd in a contradictory kind of way, but it points out the fact that the question of what's happening now at a distant location is something that requires us to have a very careful definition. Einstein's made the best definition that agrees with the ordinary way that we use time around when we aren't moving at large speeds. Right? We synchronize clocks, and that's what we would mean by simultaneous. But given the constancy of the speed of light, that seems to lead to sort of, it makes me realize that the idea of exactly if something's in the future or past relative to us right now, according to some person who's moving toward or away from it, is not something that has much sort of real importance to it, even though it sounds very fantastic. Okay, so here's just to summarize that. We've defined what it means for clocks to be synchronized, which defines what simultaneity means in an IRF. If we believe in the principle of relativity and the principle of the constancy of the speed of light, what is simultaneous in one IRF is not simultaneous by that same definition in another IRF. As a consequence, when we switch our IRF, like this fellow is doing here, we change which distant events we consider to be in our past or future. It sounds superficially amazing, but should suggest that there's very little real meaning to the location and time of events that are very distant from you. They can't have any immediate effect on you, right? So whether they happen in the future or the past, that's an idea that's in my head, but it's not something that's immediately affecting me, right? I mean, suppose some supernova goes off and it's eventually going to kill us. Well, that information is going to take a long time to get to us. And, whether it's in the future or the past, you might say, well, if it's already in the past, I don't have to worry about it. Well, no, because its effects are still heading towards us. So even though it happened a long time ago, maybe the radiation that's going to fry Earth is still heading towards us. And so it can eventually have the same effect, but that's sort of a definition. Okay, other questions on that? That's sort of a follow-on to that worksheet, and it's a lead-in to the twin paradox worksheet, which we're going to finish up with today. But here's another non-interesting result that, but we need it for completeness, that Merman chose, and that is the perpendicular case. What if we view clocks that are separated by a certain distance and they're synchronized, or there's some simultaneous events, to phrase it in the other way, the clock reads 12, but we're going to view it from a point of view that moves not along the line separating those clocks, but moves in the direction perpendicular to the clocks. And the question is, will one of them lead or will the other one lead from the other point of view? Well, so if they zoom along that direction, of course, they're going to see this meter stick length contracted along the vertical direction in my drawing here, right? But the upshot is, no, they'll still be synchronized as long as you're moving along the perpendicular direction. And that's because, well, you can consider two different inertial reference frames. And if one said, oh, the one in the direction I'm looking is reading ahead and the one behind my head is behind, this other IRF would have exactly the opposite point of view there. And they can't both be right. So it leads to a contradiction if you assume that they're simultaneous in one of the frames and they become non-simultaneous. So you can think of this as another non-effect kind of one, kind of like the meter stick moving perpendicular to its length. When events are simultaneous in one frame and they're separated by a certain distance L, if you move in the direction perpendicular to the separation of the events in which they're simultaneous, they stay simultaneous. And it's the same way with time differences between events. They would be separated by, well, let's not make it confusing here, but this is what Merman calls Rule 5. If two clocks are synchronized and separated by a distance L in their proper frame, that means the frame in which they're at rest. Then in an IRF in which the two clocks move with speed v perpendicular to the line joining them, the two clocks are also synchronized. Okay, so simultaneous events in one frame are simultaneous in another frame if that other frame is moving in the direction perpendicular to the line connecting the two simultaneous events. All right, let's finish up with one more worksheet, and this is a good follow-on to the last worksheet. This is called the twin paradox worksheet if you're pulling it up on Zoom. I'm passing it out here. This is really meant to be worked on in groups. So, if you can possibly work with someone who's somewhat adjacent to you, it just really helps to talk it out because we're going to be filling in a lot of numbers. I know we're not going to have time to get through all the numbers today, but this really gets to the heart of that weird effect that happens when the ship suddenly changed from heading towards X to leaving X. and their assessment of what was in the future changed to the past, or vice versa. I can't remember right now what the words were. Here we're going to consider two twins. The twins traditionally are called Terra, for Earth, is a twin who stays on Earth. And Stella, of course, star, the star traveler, is going to go on a distant trip at 0.866c. That's to make gamma 2. That makes your calculations a little bit convenient, okay? And they're going to go to a planet X, which is 10 light years away and as assessed by the Earth IRF. 10 light years away in the Earth IRF. And at rest with respect to Earth. So it's moving along with Earth. And the idea is, well, of course, the Earthlings are going to say Stella's clock is slow, but Stella is going to say the Earthling's clock is slow. And they're both right. And as long as they both keep moving relative to each other, they're always right, but they can't compare really easily because they just keep getting farther and farther apart. If they want to compare, they've got to come back together. And in this way, they come back together in a very asymmetric way. Terra stays on Earth and just sits at rest, or at least feels like he or she's at rest. And Stella goes out to X and immediately turns around and comes back in the other direction. And then they're going to compare their biological ages, how much time is ticked off on their clocks, every measure of time, they're all going to agree, as we've discussed, okay? Since gamma equals 2, Stella sees half the distance between Earth and X. All right, so what you're supposed to do here is imagine there's identical clocks on the rocket, so that I'm labeling as R here in this little chart down below. R is the rocket clock, E is the Earth clock, and X is the planet X clock, and they all read in years. And somehow, as assessed by Earthlings, with their notion of simultaneity, the clock on the rocket as it's leaving Earth, and the clock on Earth, and the clock on X are all reading 0 for the notion of simultaneity according to the Earthlings at the instant the rocket leaves Earth, heading towards X. So I filled in the first clock readings there, but you're supposed to fill in the other clock readings. So in other words, here's what the reading on the rocket clock, Earth clock, and X clock are at, I should stop sharing here so people at home can see what I'm pointing at. Here's what the rocket clock, Earth clock, and X clock read as the rocket leaves Earth. We want to know in the rocket as it's moving right, that's the one where it's traveling towards X, at that same event, the rocket leaves Earth, what does the rocket right inertial reference frame assess for the reading on the rocket clock, the Earth clock, and the clock at X? The rocket's not yet moving left, so that's the second half of it. So that's why I've grayed out these squares there. They don't pertain to the first two events. Later on, the rocket arrives at X, and I want you to tell me when it arrives at X, as assessed by the Earth inertial reference frame, what is at, relative to that position, what is the clock reading on the rocket, Earth, and X from the Earth point of view? What's the reading on the rocket from the rocket right point of view, where it's heading towards X and about to arrive there? What's the rocket reading, Earth reading, X reading, and so on? So rocket right means when the person is traveling out towards X. Rocket left means when they're traveling back towards Earth. The first two events don't really make sense because there isn't a rocket going left at that point in time, but it will make sense for the third and fourth ones. Okay, I'm not sure how this is going to go, but let's see if we can at least fill in the first two lines of this worksheet. I'm going to give you about 5 minutes in the breakout room, and then we'll come back and discuss the first two lines. I'm calling back the breakout room just because I want to make sure we have enough time to do some discussion together, at least for those first 2 rows of things. Okay, I called you guys back from the break room because we're almost out of time for today. And so what I'm going to do is do a little bit of discussion just for the first 2 rows that you're supposed to be filling in there. And the only reason that is reasonable is because a couple of things are pretty easy to fill in from the principle of invariance of coincidences. Okay, so we're starting out with this information filled in here. From the Earth IRF point of view, the rocket, Earth, and X clocks all read the same thing at that particular instant in time, where instant is defined by who's on Earth. An instant of time means something different in different moving frames. What do you think about the rocket, the reading of at the moment the rocket leaves Earth? From the rocket's point of view, what should the reading on the rocket clock be if the Earth said it reads 0 at that event? Yes, 0. That's the principle of invariance of coincidences. So the rocket clock has to read 0 when the rocket leaves Earth, because we're describing the same event 2 different ways. Rocket leaves Earth and rocket clock reads 0. They're both present in the same place and same time, right? So those 2 descriptions have to be the same no matter how you're moving. Okay, so the rocket's going to assess this to be 0 as well. Don't pay attention to those other numbers. I just didn't have them all scrolled in here. Same thing with the Earth clock. The Earth clock was present at both those events, right? Rocket leaves Earth and Earth clock reads 0. That was true in the Earth clock, Earth point of view, and therefore the Earth clock has to read 0 in for that same event from the point of view of the rocket moving right. Now, that's not true about the clock that's on X. Earth says that clock is, according to the Earth IRF point of view, that clock read 0 at the same instant when the rocket left Earth. As soon as you start moving right, we know our assessment of whether that point we're moving towards is in the future or in the past. And for us, the one that you're heading towards, in this case, we're taking the rocket right's point of view, it's heading towards that distant location. So the event at the distant location happens first. That's our mnemonic. We're over here asking the question, at this instant, we're here in the ship. If it already happened, if this one happens first and this one happens later, then when I'm asking that question, it's in the past. That means 8.66 years have elapsed since the amount of, since I asked, since the clock read 0 there. It all of a sudden became in the past by 8.66 years. Where did I get the 8.66 years from? It's just the LV over C squared formula, simply because we're interested in what the clock reading differences are. Not how long we have to wait, but it's the simpler formula there. Okay, what about the Earth's assessment of what the rocket clock reads when it gets to X? Okay, we're saying from the Earth's point of view, when the rocket clock reaches X, what is the rocket clock going to read? How would we calculate that? It's none of the numbers we've encountered so far here. Where did I get that 5.77? Well, I've got to calculate it. I know how fast One way to calculate it is to say, I know how long the trip is going to take from the Earth point of view. Look, they've got to go 10 light years at gamma equals 2, you know, at 0.866 c. So I can use distance equals speed times time from the Earth point of view to get the time in Earth years. What we want to know is how long the clock on the rocket started out at 0. We all agree on that. How much the rocket clock has ticked off. Can't think of the right word for it. And therefore, when we find the, well, let's see. If we use distance equals speed times time from Earth, I may be doing it a different way in my solutions here. Yeah. If we use distance equals speed times time, we have the distance they go is 10 light years at 0.866 c times t, and we can solve for the time that's elapsed in Earth. And here, I've got to then shrink that amount of time because the people traveling between those two means I need to have that number. So in the Earth assessment, when you use distance equals speed times time, you get 11.5 years, but then we have to have that number, which is 5.77 years, to get how much time is ticked off on the rocket clock. On the Earth clock, as assessed by the Earth there, that 11.5 years, whoops, right here, is just simply distance equals speed times time. And of course, the same amount of time as assessed by the Earthlings has ticked off on the clock on X because, look, they started off at 0, they're synchronized with each other, and they're both elapsing at the same rate because they're in the same IRF. So that's the kind of argument you see there. All right, we're over time now, so maybe we'll continue this discussion later, and I may just finish this discussion up at the beginning of tomorrow. So you should come to class tomorrow, and you're welcome to stop coming to class on Wednesday or Thursday when you have the Chapter 7 homework completed. But I thought it was worthwhile meeting for that. There's no new reading. I guess there is new reading, but it's just digesting the stuff we've done so far. The next chapter is objections and reflections, where now we've discussed these 3 big effects, and Merman is saying, well, look, a whole lot of stuff still doesn't make sense. Let's try to take seriously the objections that someone might raise and reflect on why we can make sense of it in terms of relativity. There's no contradictions there. So we'll maybe finish the discussion on this worksheet and find out that indeed, according to special relativity, Stella is going to age less by a factor of 2 than Terra will. The one that stays on Earth is going to be older. There's an asymmetry here because they both didn't do symmetric things. One stayed in the same IRF, one switched IRFs halfway through, and that makes all the difference. But the analysis is in the details there. Okay, don't forget, I want your Chapter 5 homework if I haven't gotten it yet, and your Chapter 6 homework. For those of you on Zoom, just email me a document with photos of your stuff in it. So if you haven't given those to me, make a pile up here. Then I can do my accounting and see whose I'm missing on the Chapter 6 stuff. Yes. Mm-hmm. Sure. Yes, please hang out if you want to do office hour questions. There was just a question about problem 6.3 on the homework. And let me see in my pile of stuff I have here where my Chapter 6 homework list is. Is it in here maybe? Yeah, I think it's in here. All right. 6.3 says, Alice and Bob are astronauts who each pilot separate rocket ships in outer space. Alice's rocket has a proper length of 50 meters. Bob's rocket is a slightly newer model with a shorter proper length. So if we place them next to each other at rest, we know Bob's is going to be shorter, and we're about to be given enough information to figure out how much shorter. Bob decides to play a trick on Alice. He zooms by her rocket with a relative speed of 0.8 c. Both rockets are oriented in the same way. In other words, Alice is cruising along and Bob is coming up with his nose of his rocket aimed in the same direction. First, the tip of his rocket passes the back of Alice's, and then later on, it passes the front of Alice's rocket. Both rockets are oriented the same way, yeah. As Bob moves by Alice, he has shipmates at the front and back of his ship make careful measurements of the length of the rocket and finds it to be the same length as his. So amazingly, he's traveling just fast enough so that from his point of view, Alice's ship is length contracted, and at the moment, according to him, the front tips align, the back tips also align at that moment, and so their lengths are the same. Okay. A then asks, what is the proper length of Bob's rocket? That means proper means when it's at rest, measuring it the normal way. Yeah, I don't have any more staples here that I see. There's tape. Or you can dog ear it. That's the best I have. Okay, so how might we do this? Well, so go ahead. Oh, I'm sorry, maybe I misread it. What is the proper length of Bob's rocket? Well, Alice's rocket has a proper length of 50 meters. We're already told that Bob's rocket has a proper length that's less than 50 meters. So when Bob is going fast enough, from his point of view, he's just at rest, right? And Alice is moving by. Alice's normally, or in the proper sense, 50-meter long rocket lines up with Bob's when it's moving at a certain speed. And so it's length contracted. And so what we want to do is figure out the length contracted length of Alice's rocket, and that will be exactly the same as the proper length of Bob's because it lines up when he's just sitting there and he, you know, from his point of view, he's not moving at all. So the length contracted length, when what we do is divide by gamma to get the length contraction. This is 0.8 c, so we've got to calculate what gamma is. In this problem, gamma is equal to 1 over the square root of 1 minus 0.8 squared. Where are my solutions? 6.3. So this number is about 1.667 gamma between the two due to their relative speed of 0.8 c. And that means that if we take Alice's rocket's proper length of 50 meters, it's going to be smaller by a factor of 1 over gamma. And that's going to be the length that Bob's has because he's just sitting there at rest and seeing the two line up at an instant in time. Okay? So what we need to do is take the length contraction of Alice's 50-meter one, and to length contract it, we simply divide by gamma. And that number gives exactly, according to my notes here, 30 meters. Excuse me. Well, probably not exactly, but at least that's, maybe it is exact. That's A. And then B, we're asked from Alice's point of view, she sees Bob zooming by in the backwards direction. Yeah, sorry. Bob sees Alice moving backwards as he passes her. Alice sees Bob going forward and makes careful measurements of the length of his rocket as it moves by. How long does she measure the rocket to be? Well, his rocket, we now just found out, has a proper length of 30 meters. So she's going to see it as shrunken compared to that, right? Smaller. So she's going to see his rocket have a length of 30 meters when she has her observers on the rocket at the front, wherever they need to be. Measure at the same time, they're going to measure 30 meters divided by 1.667. And that number, of course, is even smaller, 18 meters. Something close to 18 meters anyway. Do you want to keep going with this one, Joseph? Okay, so here, there's a little interlude here. Let's define two events. Event one is where and when the very front tip of Bob's rocket passes the back end of the tail of Alice's rocket. So event one is he first passes the rear of her rocket. Event two is when the tip of his rocket passes the front tip of Alice's rocket. So it's just where the front tip of his rocket is, at the rear of her rocket and at the front of her rocket. Okay, those are event one and event two. In Bob's IRF, what's the time interval between the two events? Well, the important thing is that there's something that's present at both events. It's the tip of the rocket, right? Because the tip of the rocket is part of the description of both events. And we know something about when time intervals between events, when one of the two moving parties was present at both events, had a single clock that was present at both events, right? So rephrasing it in terms of the way we described it in class, Earth, distant star, rocket going between, and the rocket is present at the leaving Earth and arriving at X events. Our takeaway was the rocket's going to assess less time between those two events than the Earthlings will. So here, the tip of Bob's rocket is present at both events. So that means Bob is going to assess less time between these two events than Alice is. Okay, so what do we know about now? We're asked about in Bob's IRF, what's the time interval between these two events? Well, in Bob's IRF, let's see. Alice is moving by at 0.8c, right? And I guess we have two ways we could do this. We could do it with the length contraction, or we could just use distance equals speed times time, right? Because we know the speed Alice is moving, and we know the distance that her rocket has to move, which is as she's zooming by Bob sees Alice zooming by like this, right? Event one, and then event two, the distance she moves between those two events, in Bob's point of view, is the length contracted length of her rocket. So one way to do part C, we remember gamma here. C is we're going to use from Bob's point of view, distance equals speed times time. Okay? The distance that Alice moves in between the two events, in this case, is, from Bob's point of view, is the full length of Bob's ship, which we found out is 30 meters, right? Let's see. Am I thinking about this the right way? This is from. I'm going to take this in Bob's point of view. Let's see if we're Bob's point of view. So Bob's assessment of distance moved by Alice is that in between Alice's. Oh, wait a minute. Maybe I've got this wrong. Let's draw a picture over here. So here's Bob's assessment. Bob's got a certain rocket here. We'll put a B on it. And Alice has a rocket that looks the same length as it's going by. So maybe it doesn't really matter which one we take. So here's Alice. Bob is overtaking Alice. So Alice is actually moving in that direction, right? So here's a picture of, in Bob's frame, event 2 happening. Earlier on, Alice was up here. Alice, again, is moving backwards. And Bob was feels like he's totally at rest, so he's not changing. Here was a picture of event 1. Okay, so in Bob's point of view, I'm making this, it sounds like too difficult. In Bob, if we're talking about the time interval here, right? So Bob was the one present at both events, so he's going to measure a shorter point of view. If we want to know the distance as assessed by, sorry, not the distance, the time interval between the two events as assessed by Bob, we could just look at how far Alice moves during that time. And Alice moves a distance in between the two events of the length of her rocket ship, as assessed by Bob, right? So Bob is saying Alice's rocket ship is length contracted to a length of 30 meters. And so this is from Bob's point of view, where Bob's just sitting at rest. Bob's overtaking Alice, but he sees Alice as sliding backwards like this, right? And Alice moves a distance of 30 meters in between event 1 and event 2 at a speed of 0.866 c, right? No, 0.8 c. So using distance equals speed times time. She moves a distance of 30 meters. The speed he sees her going at is 0.8 c. 3 times 10 to the 8th meters per second. And the time as assessed by Bob, maybe I'll write that as T Bob, we can solve for by doing a little division. And that's 1.5 times 10 to the minus 8 seconds. It doesn't take long because they're moving so fast with respect to each other. Because when we divide by that 3 times 10 to the 8th, of course, we get something tiny. So the answer to C is T Bob is 1.5 times 10 to the minus 8 seconds. Questions on that one, Joseph? Does rather than 1.5 as the prefix there? If you guys are doing it, I believe you. I probably just wrote it down the wrong way. You're saying that's the correct answer? 1.25 times 10 to the minus 8th? I mean, if 2 of you got it, I believe it. I can try it in my calculator, but I believe it. Okay, clear. Okay, so if we do 30 divided by 0.8 divided by 3e8, 1.25, and times 10 to the minus 7. Huh, I've got it written right next to the correct equation, so I better circle that in my solution and correct it before I scan them and post them. That would be embarrassing. Okay, so yes. Not sure where that number came from, but this is what I have written next to it, which just seems like I flubbed it in the calculator. Okay, that's C. D is easy. As assessed by Bob in Bob's IRF, what's the distance between these two events? No. Although that seems like a reasonable answer. Here's Bob's point of view. Bob's standing on the front of his ship. Front of my ship aligns with the rear of Alice's ship. There's an event that happens. Alice is moving by. Front of Alice's ship aligns with the front of my ship. There's another event. They both happen right under my feet. So in Bob's point of view, there's 0 distance between those events. Because from Bob's point of view, the 2 events are happening at the same location in his, on his meter sticks or whatever. Always at the front of the ship. And from his point of view, he's just not moving. So the 2 events that are defined by the front of his ship happen at the same location. Okay, in Alice's IRF, what's the time interval between the two events?
Should we do the one like T equation stuff? Like the I don't know.
Yes, so we could say, in this case, Bob was the one who was at the same location. These two events were at the same location for him. And we found out how much time, now that we've correctly calculated it, Bob assessed happening between those two events. We said that was the one case where we could just simply use the length contraction, the time dilation formula to assess how much time is experienced by the other point of view. Now remember, the person who's present at both events always measures the shorter amount of time as having elapsed. That was just the way it worked out. The other way, it seems like it would be like that, but we have to take into account the asynchronization of the clocks. So we found out Bob says this amount of time elapsed. That's the shorter of the two times. The two times are going to differ by a factor of gamma. You either multiply by gamma or you divide by gamma. And this is the smaller of the two. So if we want to make it bigger, we need to multiply by gamma. So that means that to do E, we can just multiply Bob's time. T Alice is going to be equal to gamma times T Bob. Suppose I need to check my number on that one. Oh, I use distance equals speed times time for that one too. Sometimes you've already figured out the distance, you can back it out, because we know in Alice's frame, Bob's ship has to move, the tip of his ship has to move the full length of her ship, which is 50 meters. So in Alice's frame, the tip of Bob's ship is moving 50 meters, that would go here, at 0.8 C, and we can solve for T-Bob. And the factor of gamma comes in there because we used gamma to get that 30 meters already. So we should get the same answer either way. According to me, I get 2.08 times 10 to the minus 7. So it looks like this, since I didn't use the gamma formula we were talking about here, I got it right because I wasn't relying on my other incorrect number there. Okay, and then finally, what's the last one? In Alice's IRF, what's the distance between the two events? Well, one event is at the front of Alice's ship and one's at the back of Alice's ship, right? Because it's the front of Bob's ship that is present at the front of Alice's ship and at the back of Alice's ship. Alice's ship is 50 meters long, proper length, right? And she's just sitting there looking at it at rest. So it's got to be 50 meters between the two. I know, it's going to take some practice to really, it's so easy to be tricked into the wrong way of thinking about these kinds of things, which is why we're at a good place now in the course in that we can try to digest some of these things over the rest of this week. And if these three effects were the only thing you came away from this course with, that would be a good, outcome of the course. Now, of course, I want to learn about a few other things, but these are the main three effects that Merman's talking about. And so if we can get a satisfying hold on these, even though they really